welcome to the deep dive.
Great to be here.
Today, we're plunging into something pretty electrifying. The hunt for superconductivity at higher temperatures.
That's right. You know, that state where electricity just flows completely unimpeded, zero resistance.
Exactly. And the potential is just huge. Think lossless power grids, super powerful magnets for, say, smaller MRIs, maybe even the guts of future quantum computers. Really revolutionary stuff.
It absolutely is. But, well, there's always been a catch, hasn't there?
The temperature.
Yeah. Usually this magic only happens at incredibly cold temperatures, like fractions of a degree above absolute zero.
Which, practically speaking, is a huge barrier. You need some serious expensive cooling.
Right. It limits where you can actually use it.
But that picture's been changing, hasn't it? With these hydrogen-rich compounds?
Oh, definitely. We've seen hydrogen sulfide, H₃S, go superconducting at 203 Kelvin.
Which is what, minus 70 Celsius? Pretty amazing compared to near absolute zero.
And then lanthanum dikahydride, LaHero, pushed it even higher, 250 Kelvin.
Wow, okay, that's minus 23 C, getting closer.
And crucially, both of those are way above the boiling point of liquid nitrogen, which is 77 Kelvin.
Making them much more practical, potentially. That's why we call them high-temperature superconductors, even though they're still pretty cold for us.
Exactly. And today, we want to focus on something really fundamental about them.
All right.
The superconducting gap. You can think of it as like a core signature of that superconducting state.
Right. It tells you something deep about how the electrons are behaving.
Precisely. And the big news is scientists have finally measured this gap in H₃S.
Ah, okay. So that's our source material for this deep dive.
Primarily, yes. A study in Nature from April 23rd, 2025. It's called Superconducting Gap of H₃S measured by tunneling spectroscopy.
Okay, tunneling spectroscopy. But why was measuring this gap such a big deal? Why so difficult?
Well, it comes down to how you make these materials in the first place.
The pressure, right?
Extreme pressure. We're talking over 1 million times the air pressure around us right now.
1 million atmospheres. How do they even do that?
In these tiny devices called diamond anvil cells, squeezing a minuscule sample between two diamonds.
Wow. Okay, I can see how trying to poke around and measure something like a superconducting gap in that environment would be, well, tricky.
Extremely tricky. Your standard tools, things like, scanning tunneling microscopy or ARPES.
Angle-resolved photoemission spectroscopy.
Yeah, those just don't work under that kind of massive pressure. They aren't built for it.
So they needed a whole new approach.
They did. Researchers at the Max Planck Institute in Mainz basically invented one.
Oh, really? What did they come up with?
A technique they call planar electron tunneling spectroscopy, specifically designed to work inside those diamond anvil cells.
Okay, that sounds ingenious. So our mission for this deep dive is clear. We need to understand this first ever measurement of a superconducting gap in H₃S using this new technique. What did they find? And crucially, what does it actually tell us about this whole high-temperature superconductivity puzzle?
Right. Well, the headline finding is they did it. They successfully used their technique to measure a fully open superconducting gap in H₃S.
And what was the value? Do we have a number?
We do. It came out at approximately 60 millielectron volts.
60 MeV.
Okay, 60 MeV is that big, small, what's the context?
It's a substantial gap. And importantly, they also looked at its chemical cousin, deuterium sulfide.
DA.
Right, deuterium being the heavier version of hydrogen with an extra neutron.
Exactly. And in DS, they measured a gap too, but it was smaller.
Oh, much smaller.
Around 44 MeV. So 60 for AAs, 44 for DS.
Okay, just managing to measure anything under that pressure is amazing. But that difference, 60 versus 44, that feels significant. Why does the gap change when you just swap hydrogen for deuterium?
Well, that's the really crucial part. It points directly towards the mechanism driving the superconductivity.
How so?
The prevailing theory for these hydrides is that it's driven by the interaction between electrons and phonons.
Phonons, okay. Those are the vibrations of the atoms in the crystal lattice, right?
Exactly, like tiny vibrations shaking through the material. The idea is that these vibrations can mediate an attraction between electrons, allowing them to pair up.
The Cooper pairs. I remember those. Electrons that normally repel each other somehow team up.
Precisely. They form these bound states, Cooper pairs, which can then move through the material without any resistance. It's like they glide.
Okay. So how does the superconducting gap fit in with Cooper pairs?
The gap is essentially the energy cost to break a Cooper pair apart. the minimum energy you need to inject to split those paired electrons back into individual ones.
Ah, I see. So measuring the gap confirms the pairs exist and tells you how strongly they're bound.
Exactly. The size of the gap is like a fingerprint. It reflects the strength of the interaction that's pairing them up.
Okay, so back to the ACE versus DS difference. Hydrogen is lighter than deuterium.
Right. And lighter atoms vibrate at higher frequencies. Think of like guitar strings, thinner strings vibrate faster.
Okay, so H vibrates faster than D in the lattice.
And if those vibrations, the phonons, are what's causing the electron pairing?
Then changing the vibration frequency by swapping H for D should change the pairing strength.
You got it. And therefore, it should change the energy needed to break the pair, the superconducting gap.
And that's exactly what they saw. A smaller gap for the heavier, slower vibrating deuterium version.
Precisely. This isotope effect, as it's called, is really strong evidence that the electron-phonon interaction is indeed the mechanism at play in H₃S. It matches the theoretical predictions beautifully.
Wow. So it's not just getting a number, it's like experimental proof for the theory.
It's a huge piece of validation, yes, for the models explaining superconductivity in these hydrides.
That's fantastic. And the implications must be pretty broad then. This isn't just about H₃S anymore.
Not at all. It really lays the groundwork. Now that we have a tool, this planar tunneling spectroscopy, that can actually probe this fundamental property under pressure.
We can use it on other hydrides.
Exactly. We can start to systematically investigate this whole family of materials, maybe figure out what specific factors, what kind of atomic structures or vibrations lead to even higher transition temperatures.
Chasing even higher T's.
Yeah.
That leads straight to the practical dream, doesn't it? I remember reading a quote from one of the researchers, Dr. Feng Du.
Yes, he expressed exactly that hope, that by extending this technique, they can sort of, zero in on the key ingredients.
To find materials that work at higher temperatures.
Yeah.
And crucially,
at lower pressures. That's the ultimate goal, right?
Oh.
Materials that are superconducting closer to room temperature and normal atmospheric pressure. Imagine that.
it would change so much. Energy, computing, transport. But what about Dr. Mikhail Arametz, a real giant in this field, sadly passed away, but his work was foundational. Did his group comment?
Yes, his perspective came via Vasily Minkov, the project leader now at Max Planck, and it was powerful. Dr. Aram has apparently considered this measurement the most important work in the field of hydride superconductivity since the discovery of superconductivity in H₃S in 2015.
Wow. High praise indeed, coming from the group that made that initial discovery.
It really highlights how significant this step is. It brings that vision, Aramet's vision, of room temperature, moderate pressure superconductors just that little bit closer.
Okay, so let's quickly recap this deep dive. We've explored how scientists overcame incredible technical challenges, extreme pressures in diamond anvil cells, to measure the superconducting gap in H₃S for the first time.
Using their novel planar tunneling spectroscopy technique.
Right. They found a gap of about 60 MeV in H₃S and a smaller one, around 44 MeV, in its heavier counterpart, DS. And that difference, the isotope effect, strongly supports the theory that lattice vibrations, phonons, are the key mechanism binding electrons into Cooper pairs in these materials.
Providing crucial experimental validation. It's not just a theory anymore. We're seeing its fingerprint directly.
And this opens the door to systematically studying other hydrides, hunting for the secrets to even better superconductors, ones that might one day operate under practical conditions.
It's a major leap forward, no question.
So here's a thought to leave you with. We just saw how an innovative technique broke through a barrier measuring something fundamental under previously impossible conditions. Makes you wonder, doesn't it? What other scientific walls, things that seem insurmountable today, might crumble next if we just find the right, clever approach? What kind of technologies, maybe things we can barely even imagine now, could that unlock?
It's certainly exciting to think about.
Indeed. Thanks for joining us for this deep dive.